Hello my precious friends, I really hope that you are doing great. Welcome to our today's class. It is our 7th lesson on the 7th topic of Form 3 work, which is called Electrostatics 2. As usual, let me commence by giving the quote of the day, which states that tearing someone else down doesn't build you up. We shall discuss that quote at the end of our class today. So today we're looking at the second way of connecting capacitors. So the first way was actually series connection. So the second way in which we can connect capacitors is in parallel connection of capacitors. So whenever capacitors are connected in parallel, it simply means that they are connected across each other and across our battery or across our source of power. So whenever capacitors are connected across each other, such as the ones shown in this particular diagram, then we say they are said to be in parallel connection. So just like in resistors, when components are connected in parallel to each other or parallel to the source, it simply means that the potential difference across each capacitor or across each component will be the same as the EMF or the potential difference across the source. So whenever components or capacitors or even resistors, whenever they are connected across each other or when they are connected in parallel, then the potential difference across each capacitor will be the same. So that is to say that V total, that is the voltage across the source, must be equal to the voltage across the first capacitor, must be equal to the voltage across the second capacitor, must be equal to the voltage across the third capacitor. So the total voltage across this particular battery must be equal to the voltage across our first capacitor C1, must be equal to the voltage across the second capacitor C2, must be equal to the voltage across the third capacitor, that is C3. So for any parallel connection of components, the total voltage entering a junction must be equal to the voltage across each and every component within that particular junction. Then also under resistors, we said that when resistors or when components are connected in parallel, then the total current entering a junction must be equal to the sum of the current across all those components that are connected within that particular junction. So for resistors, for example, we said that the total current entering a junction must be equal to the sum of the current drops across each component in that particular junction. Then from cells and simple circuits, we did say that charge can be given by the product of current and time. So if Q is equals to IT, that is if charge is equals to the product of current and time, if I hold T constant or if I hold time constant, it simply means that charge will be directly proportional to the current. So that simply means that the way current was behaving, that is for the resistors, is the same way that charge will also behave for the capacitors. So remember, for the resistors or for any other components, we said that the total current entering a junction must be equal to the sum of the current drops across each component within that particular connection or within that particular junction. Therefore, the same way that current was behaving for resistors is the same way that charge will behave for the capacitors, simply because charge and current are directly proportional to each other, courtesy of this particular formula which you obtained from that is cells and simple circuits. So therefore the current I total was equal to I1 plus I2 plus I3. That is when we were looking at resistors. Similarly, the charge, that is the Q total, must be equal to Q1 plus Q2 plus Q3. That is the total charge will be equal to the sum of the charge across those particular capacitors. So if you want to find the total charge through this particular battery, you will simply take the charge Q1 plus Q2 plus Q3, or the charge across each of the capacitors. Then since Q is equals to CV, remember this is also a formula that we obtained from when we were introducing capacitance. We said that capacitance is simply the voltage, that is the charge per voltage, charge per unit voltage. So capacitance was actually Q over V. Therefore, Q is equals to the CV. So the charge Q is given by capacitance times the voltage. So from the equation Q is equals to CV, equation 2 will become, so remember equation 2 is this particular equation here, that Q total is equals to Q1 plus Q2 plus Q3. So because Q is equals to CV, this particular equation will become, so Q total will simply be C total times V total. Therefore, Q total is actually C total times V total. Then Q1 will be equal to, remember Q is CV, so Q1 will just be C1 plus V1. So Q1 is C1 plus V1. then plus Q2. So Q2 will just be C2 plus V2 because Q is equals to CV. Then of course Q3 will simply be, that is Q3 will simply be C times V, which is C3 times V3. So Q3 is just C3 times V3. So this forms our third equation. So from equation Roman 1, remember equation Roman 1 was for the voltage, that V total is equals to V1 is equals to V2 is equals to V3. So because from equation 1, V total is equals to V1 is equals to V2 is equals to V3, we can actually equate it to a constant. For example, we are equating to a constant K, because after all they are equal. That is V total, the voltage through the source, is equals to the voltage across the first capacitor is equals to the voltage across the second capacitor is equals to the voltage across the third capacitor. So if we let the voltage, the V total, which is equals to V1, which is equals to V2, which is equals to V3, if we let it be equal to a constant K, therefore it means that our equation Roman 3 will simply become, so this was our equation Roman 3. So where I have V total, I'll just substitute with K, because V total is equals to K. So this part will become C total times K, because my V total is equals to K. So this will become C total times K. Then of course it was is equals to C1 V1. So also remember V total is equals to V1, which is equals to K. So V1 is also equal to K. Therefore this part will become C1K, hence C1K. Then plus C2 V2. Remember also V2 is equals to K, because after all they are equal. Therefore this part will simply become C2K. So this is C2K. Then plus C3 V3. Then remember V3 is also equal to K. Therefore this part will become C3K. So this is a C3K. Then if I divide, because K is common in the first term, the second term, the third term, and also the fourth term. So because K is common, I can just divide each and every term by K, because it is common, so that we can eliminate it. So dividing through this particular equation by K, we shall have, of course, if we divide through by K, the K will just cancel out. So CTK divided by K, you'll just obtain CT, because K and K will cancel. C1K divided by K, you'll just obtain C1. C2K divided by K, you'll obtain C2. Then C3K divided by K, you'll obtain C3. So because K is common, if I divide through by K, the K will cancel out, so that this equation becomes CT is equals to C1 plus C2 plus C3. Therefore, this is the equation that we use to find the total or the combined or the effective capacitance for any capacitors which are connected in parallel. Therefore, for any parallel connection of capacitors, the effective or the combined or the total capacitance is given by the formula C total is equals to C1 plus C2 plus C3. That is depending with the number of capacitors that you have. So for any parallel connection of capacitors, these are the things that you need to know. You need to know that V total is equals to V1 is equals to V2 is equals to V3. You also need to know that Q total, you simply take the sum of the charge across each capacitor. Then if you want to find that is C total, you simply take C1 plus C2 plus C3. But if you want to find the total charge, you also add the sum of the charge across each of the capacitors which are in that is parallel connection. Then, so that you don't confuse between resistors and capacitors, because it is easy to confuse between the formulas of resistors and capacitors, I have a small table here which is giving you a comparison between resistors and capacitors, so that you don't confuse between the two, because I find most students are confusing the formulas for the calculation of effective capacitance and also for the effective resistance. So for any series connection of resistors, we did say that V total will be equal to V1 plus V2 plus V3. Similarly, for any series connection of capacitors, V total or the effective, that is the total voltage, will simply be equal to V1 plus V2 plus V3. So they are exactly the same for resistors and capacitors. Then we said that for any series connection of resistors, I total, that is the current entering a junction, will be equal to the current across each and every component within that particular junction. That is I total is equals to I1 is equals to I2 is equals to I3. Then we have said that from current electricity, that is from cells and simple circuits, we did say that Q is equals to IT. Therefore, if you hold time constant, then charge must be direct proportional to current. Then you have said that the way current was behaving for resistors is the same way that charge will behave for the capacitors. Therefore, because the I total was equals to I1 is equals to I2 is equals to I3, it means that when we come to capacitors, Q total must be equal to Q1 must be equal to Q2 must be equal to Q3. That is, it is behaving in the same way that the current was behaving for the resistors. Then the total resistance for the resistors which are connected in series, R total, we are taking the sum of the resistances of the individual resistances. If you want to recall this, you can just revisit our lessons on current electricity 2, which was actually a Form 3 topic covered in this particular channel. So under that topic, we did say that the effective or the total resistance, R total, for any resistors connected in series will be R1 plus R2 plus R3, depending with the number of resistors. Now, for the capacitors, if you want to find the total or the effective capacitance or the combined capacitance, you simply take the reciprocals. So for any capacitors which are connected in series, the effective capacitance will be 1 over C total, that is the effective capacitance or the combined capacitance will be equal to 1 over C1 plus 1 over C2 plus 1 over C3. Then for any parallel connection, that is for resistors and capacitors, for any parallel connection of resistors, we did say that V total must be equal to V1, must be equal to V2, must be equal to V3. The same thing happens for capacitors. For any parallel connection of capacitors, V total must be equal to V1, V equals to V2 is equals to V3. So you can see that they are behaving exactly in the same way. Then the way current was behaving for parallel connection of resistors is the same way that charge will behave for parallel connection of capacitors. So for resistors, we did say that I total must be equal to I1 plus I2 plus I3. That is the current entering a junction for any parallel connection must be equal to the sum of the current of, that is the current drops across all the components which are in that particular junction. So since Q is directly proportional to current, so the charge will behave in a similar way. That is for capacitors which are connected in parallel. So Q total will simply be Q1 plus Q2 plus Q3. So it is behaving in the same way as current. Then for resistors which are connected in parallel, we did say that 1 over R total will be equal to 1 over R1 plus 1 over R2 plus 1 over R3. Then for the capacitors which are connected in parallel, C total or the effective or the combined capacitance, you will simply take the sum of the capacitance of the capacitors which are connected in that particular circuit. So actually, the key things to note here is that the way current was behaving for resistors is the same way that charge will be behaving for capacitors. Then the only thing that will change is how to find the total or the effective resistance and the effective capacitance. So the way resistors was behaving, to find the R total, we were taking R1 plus R2 plus R3. That is for series connection. So the same way that resistors were behaving for series connection is the same way that capacitors will behave for parallel connection. So actually, this is where we have a swap. So the way resistors were behaving for series connection is the way capacitors will behave for parallel connection. Then the same way that capacitors will behave, or the same way that resistors were behaving for parallel connection is the same way that capacitors, that is the same way that resistors were behaving for parallel connection is the reverse of how, or is the same way that capacitors will behave for series connection. So you can actually see the difference between the two. So this table should help you not to mix up between resistors and capacitors. Next, let's look at an example involving parallel and series connection of capacitors. So the example reads that the figure below shows 3 capacitors connected to a 12 volts battery. Use it to determine part A, the combined capacitance. So before you even tackle that question, there are a few things you need to remind yourself, that for any series connection of capacitors, then V total must be equal to V1 plus V2 plus V3. Then Q total must be equal to Q1 is equals to Q2 is equals to Q3. Then 1 over C total is equals to 1 over C1 plus 1 over C2 plus 1 over C3. Then for any parallel connection of capacitors, V total is equals to V1 is equals to V2 is equals to V3. Q total is equals to Q1 plus Q2 plus Q3. Then C total is equals to C1 plus C2 plus C3. Then you also need to remember the equation for the charge, which was Q is equals to CV. So these are the facts that you need to remember whenever you are calculating, you are taking any calculation involving capacitors. So this is our figure. So part A, they want us to find the combined capacitance. So the first thing, we'll combine the capacitors which are in parallel so that they go to a series way, just like we were doing under that is under current electricity 2. That is when we were dealing with the resistors. Actually, the working is the same. It is only the formulas that are changing slightly. So we'll combine the 5 microfarad capacitor and the 3 microfarad capacitor into a series form. So if because 3 and 5 are actually in parallel connection, or they are connected across each other, we shall use the formulas for parallel connection. So because we want to find the combined capacitance, or the total or the effective capacitance, I'll go for the formula involving the combined, that is the parallel connection of capacitors. Therefore, C total must be equal to C1 plus C2. So for the 5 and 3 microfarad capacitor, because they are in parallel connection, then capacitance through the 5 microfarad and the 3 microfarad capacitor must be equal to the capacitance through the 5 microfarad capacitor plus the capacitance through the 3 microfarad capacitor, which is just 5 microfarad plus 3 microfarad, which will give us 8 microfarad. But we know, so they want us to find the combined, or the total capacitance. So 5 and 3 are combined to form a 3, that is to form an 8 microfarad capacitor. So it means our circuit will disintegrate into this format, because 5 and 3 have combined to give us 8. So you can see now we have our 4 microfarad and 8 microfarad resistor. Remember, the 8 is just a combination of 5 and 3. So you can clearly see that our 4 microfarad capacitor and 8 microfarad capacitor are actually in series connection. Therefore, to combine these two, we shall use the formula for the series connection of capacitors. So for any series connection, 1 over C total must be equal to 1 over C1 plus 1 over C2 plus 1 over C3. Because we have only 2 capacitors which are in series connection, we shall say that 1 over C total must be equal to 1 over C through the 4 microfarad capacitor plus 1 over C through the 8 microfarad capacitor, which is just equal to 1 over 4 plus 1 over 8, which gives us 3 over 8. So if 1 over C total is equals to 3 over 8, if I take reciprocals on both sides, I'll simply have C total divided by 1, which is just C total, being equal to the reciprocal of 3 over 8, which is just 8 over 3. So C total is equals to 8 over 3 microfarad. But in physics, it is always good to work with SI units, and we know that the SI unit for capacitance is simply the farad. So we'll convert the microfarad into the farad. So again, we know that 10 power 6 microfarad is equals to 1 farad. What about 8 over 3 microfarad? So it will just be 8 over 3 microfarad divided by 10 power 6 microfarad times 1 farad. Then whenever you divide, if you take that is the divided number, if you take it to the numerator, it becomes a multiplication, or whenever you divide, you multiply by the then you multiply by the reciprocal. So when the power comes to the numerator, it will become a negative, so that we have 8 over 3 times 10 power negative 6 to convert it into farad. So to convert the microfarad into farad, you just multiply it by 10 power negative 6. So this is now in farad. But in physics, it is always good to leave your answer in decimals. So I'll leave it in standard form. So 8 over 3 multiplied by 10 power negative 6 into standard form, we shall have 2.667 times 10 power negative 6 farad. So I've just expressed it in standard form. Again, it is also correct to 4 significant figures. Then part B, they want us to find the charge through the 4 microfarad capacitor. The charge through the 4 microfarad capacitor. So remember, from the initial diagram, the 4 microfarad capacitor was actually in series connection with our battery. Then we know that for any series connection, Q total must be equal to Q1, must be equal to Q2, must be equal to Q3. Therefore, the easiest way of finding the charge through the 4 microfarad capacitor, to find the charge through the 4 microfarad capacitor, we shall just find the charge through the total, or the charge through the source. Then it is easier to find the charge through the source because you already have the voltage through the source, and you also have the capacitance through the source. And remember, charge Q is equals to CV. Therefore, if we have C and V, it is easier to find the charge. So the charge through the 4 microfarad capacitor is equal to the charge through the source, or is equal to Q total. The reason being, the 4 microfarad capacitor, initially it was in series connection with our source, or it was in series connection with the battery, or it was connected along the battery. Therefore, the charge through the 4 microfarad capacitor is equal to Q total, and we know that Q total, because Q is equal to CV, so Q total will just be CV, C total times V total. So that is C total times V total. Therefore, C total is just the capacitance through the, that is the total capacitance, which we have computed up here as 8/3 times 10 power negative 6. Remember, I'm not using this particular value because it is an approximated value. So if you have any calculation that you want to use the previous answer in your next calculation, always use the actual value to avoid what we call approximation or premature approximation. So I'll use this exact value because this is not approximated, but this value is approximated. So I'll use the exact value. So the C total was actually 8/3 times 10 power negative 6 farad. So 8/3 times 10 power negative 6, that is farad, which are the SI units. Then times V total. V total through the source we were given as 12 volts. So times 12 volts. So 8/3 times 10 power 6 times 12. Of course, 3 goes into 12 4 times. Then 4 times 8, you'll simply get 32. So we'll have 32 times 10 power negative 6. So I'll express it into standard form so that I get, that is 1 decimal. We'll move the decimal here so that we have 3.2 times 10 power negative 5 coulomb as our value, that is in standard form. Again, if you have any challenges in expressing numbers to standard form, you can just revisit our lessons on measurement 2, which was actually, I think, the second topic under form 2 work, which is also covered in this particular channel. So this is our charge. So the charge through the 4 microfarad capacitor is equal to the charge through the source because it was initially connected in series with the source. So the charge through the 4 microfarad capacitor is just 3.2 times 10 power negative 5 coulomb. Then part C, they want us to find the potential difference across the 5 microfarad capacitor. So remember, the 5 microfarad capacitor is found within the 8 microfarad capacitor. So the easiest way of finding the voltage or the potential difference across the 5 microfarad capacitor, we'll first of all find the potential difference across the 4 microfarad capacitor. So from Q is equals to CV, to find V through the 4 microfarad capacitor, we need to have C and Q. But you already have the Q through the 4 microfarad capacitor. We also have the C through the 4 microfarad capacitor. So from this formula, if I make V subject of the formula, I'll simply divide both sides by C. Therefore, V will be equal to Q over C. So the voltage through the 4 microfarad capacitor will be equal to the charge through the 4 microfarad capacitor divided by the capacitance through the 4 microfarad capacitor. Then, of course, we are also working with SI units. So the charge through the 4 microfarad capacitor was equals to the charge through the source, which is actually 32 times 10 power negative 6. So let me use this particular value because my 10 power negative 6 will cancel somewhere. So I'll use this value. So Q total is just equal to the Q through the 4 microfarad capacitor, which is 32 times 10 power negative 6. So the charge through the 4 microfarad capacitor is 32 times 10 power negative 6 capacity. That is coulomb, divided by the capacitance through the 4 microfarad capacitor, of course, is just the 4 farad. But the 4 microfarad. But because microfarad are not the SI unit for capacitance, I'll convert it into its SI unit, that is the farad. We know that 10 power 6 microfarad is equals to 1 farad. So what about 4 microfarad? So that will be 4 microfarad divided by 10 power 6 microfarad times 1 microfarad, which is just the same as saying, if you take 10 power 6 into the numerator, the power will become a negative courtesy of the loss of indices, so that we have 4 times 10 power negative 6 farad. That is, if you multiply times 10 power negative 6, this one is just to convert the 4 microfarad capacitance into its, that is into its SI unit, which are the farad. So these are now 4 times 10 power negative 6 farad. So the voltage through the 4 microfarad capacitor will just be 32 times 10 power negative 6, that is coulomb, divided by 4 times 10 power negative 6 farad. Of course, 10 power 6 power negative 6 and 10 power negative 6 will cancel out. That is why I used this particular term here and not the final term, because 10 power negative 6 will just cancel out. So 10 power negative 6 and 10 power negative 6 will cancel out. Then 32 divided by 4, you'll simply get 8. So the voltage through the 4 microfarad capacitor is 8 volts. So the reason for me finding the voltage through the 8 microfarad capacitor is so that to make my work easier. Because once I have the voltage through the 4 microfarad capacitor, it will help me to find the voltage through the 8 microfarad capacitor. And remember, the voltage through the 8 microfarad capacitor will be the voltage through the 4 microfarad capacitor, because the voltage through the 5 microfarad capacitor, because the 5 and the 3 microfarad capacitor are the ones which have formed our 8 microfarad capacitor, because they were in parallel connection. So I'll first of all find the voltage through the 8 microfarad capacitor. And of course, you can see the 4 and the 8 microfarad capacitor are in series connection. And you have said that for any series connection, V total must be equal to V1 plus V2 plus V3. Therefore, the V total must be equal to the voltage through the 4 microfarad capacitor plus the voltage through the 8 microfarad capacitor. The reason being, the 4 and the 8 microfarad capacitor are in series connection with our source or the battery. Then of course, V total we are given as 12 volts. That is from the initial question. The V total was 12 volts is equals to the voltage through the 4 microfarad. We have already computed it as 8 volts. We have computed it up here as 8 volts plus the voltage through the 8 microfarad capacitor. So I'll just make V through the 8 microfarad capacitor subject of the formula, so that I have, by taking 8 towards the left hand side, so that I have the voltage through the 8 microfarad capacitor being equal to 12 minus 8, which is just equal to 4 volts. But remember that the 8 microfarad capacitor was actually a combination of 5 and 3 microfarad capacitor. That is, when we combined those two, that is when we obtained the 8 microfarad capacitor. And remember, the 5 and 3 microfarad capacitor, they were in parallel connection. And you have said that for any parallel connection, V total must be equal to V1, must be equal to V2, must be equal to V3. That is, the total voltage entering a junction must be equal to the voltage across each component for any parallel connection. And remember, the voltage that is entering this junction is the voltage that has remained after the one that has dropped through the 4 microfarad capacitor. So the voltage that remained after dropping through the 4 microfarad capacitor was actually the voltage through the 8 microfarad capacitor, which is 4 volts. Therefore, the remaining voltage will enter this particular junction. And the voltage that is entering this junction is the voltage through the 8 microfarad capacitor, because the 8 microfarad capacitor is the combination of these capacitors which are actually in parallel connection. Therefore, the voltage through the 8 microfarad capacitor is equals to the voltage through the 5 and the voltage through the 3 microfarad capacitor. The reason being, the 5 and the 3 are in parallel connection. Therefore, the current, the voltage, that is, the voltage entering this junction is equals to the voltage through the 8 microfarad capacitor. And for parallel connection, V total must be equal to V1, must be equal to V2, must be equal to V3. Therefore, the voltage through the 5 microfarad capacitor must be equal to the voltage through the 3 microfarad capacitor, must be equal to the voltage through the 8 microfarad capacitor, because 8 microfarad capacitor is the combination of these two, and because they are in parallel connection, V total must be equal to V1 is equals to V2 is equals to V3. So the voltage through the 5 microfarad capacitor is equals to the voltage through the 3 and the voltage through the 8, because they are in parallel connection, which is equals to the 4 volts, because the voltage through the 8 was actually 4 volts. Next, lastly, I have an exercise that I recommend you should try at your own free time to get your understanding of the questions that you have just solved. And of course, if you have any challenges in handling any of the question, feel free to drop a comment specifying the question that you need help in. And of course, I'm always here to try and help where possible. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that tearing someone else down doesn't build you up. So the quote is warning us against being dream killers. It's encouraging us to be happy for other people's success instead of being jealous. Remember that every time you discourage someone from pursuing their dream, you are also limiting your own growth, because the success of their dream would have inspired you to also believe that your dreams are achievable. And lastly, recall that jealousy, hate, and discouragement usually destroys the vessel that stores them. Therefore, Do not allow your heart to be destroyed by these three vices. Thank you very much for accompanying me until the end of this particular lesson. I do not take it for granted. In case you're new to the channel, kindly hit the subscription button and also turn on the notification bell so that whenever I upload a new video, you'll get notified. If you know any student that you honestly think could benefit from this content, kindly share my link to them. Until next time, this is Kind Tuition Academy.